This is a monthly seminar series of the UK Next Generation Networking Group. KK needs no introduction, but very briefly, he's a professor of computer science at UC Riverside. Before this, he was a distinguished member of technical staff at AT&T Labs, and he has done a whole bunch of very foundational stuff, including the deck-bit congestion avoidance protocol, for which he got the SICOM Test of Time Paper Award. He's published over 300 papers. He's also been instrumental in other things such as ECN and so forth. And today he's going to be talking to us about his current work on serverless computing. Over to you, KK.
Thank you very much, Nishant, and thanks to you and Ignacio for the invitation. If you don't mind, I'll cut out the video so that my audio quality will be as best as my wireless can sustain.
That's perfect. And I can ask any questions that may pop up in the middle.
Yeah, I can't see the chat or anything. So
yeah.
Okay. So, you know, what is the reason for talking about cloud computing and serverless? If you look at networking, the main driving force there is, from a performance standpoint at least, is multiplexing gain. And you know, when I started looking at cloud computing and virtualization, clearly, you know, being able to do multiplexing on a compute platform was one reason. And serverless computing is really pushing that further in the sense of being able to multiplex even more. So I'm hoping that this will be reasonably interesting for you folks in the networking community as well. I've been sort of putting one foot into this cloud computing space for the last little while, working with Tim Wood, who was with me when he was doing his PhD in more than a decade ago, and he and I have been working together since then. And much of this work has been done by my students, especially Shishon Chi and Guillaume, Elizabeth, all the others have all been working on this topic as well. So our focus has been on seeing how we can make serverless frameworks use resources more efficiently and also being more responsive and fair. This was driven by wanting to use serverless computing in edge clouds that may be more resource constrained, and also by a desire to support IoT traffic better. So a number of us in UCR have been working on this, along with Tim and his student. So if you look at why serverless has been growing in popularity, I think, you know, in spite of all the performance reasons, from a user perspective, it helps ease the task of the user to develop and deploy applications in the cloud. And users only have to write the application function code. Even though they may be short-lived, these serverless functions are really helped a lot by the movement to lightweight containers. And users take advantage of this microservice paradigm to develop complex applications as a composition of individual functions. So serverless functions are typically characterized by being event-driven and being stateless. So if you look at the overall architecture for serverless, what we see, and this is a typical architecture based on Knative, and the reason we think about Knative is because that's a serverless platform that's open source, and a lot of people in the community have been working on it. So you have multiple nodes, including a master node that contains control plane components, and a number of worker nodes which are used to run serverless functions. So functions are spread across different containers and worker nodes and communicate with each other over a container network interface like, say, Flannel. If you look at an abstract view of the data and control plane, there are several key components that I show here in this abstract figure. The function pod, obviously, is the key component that does the application execution. And a serverless function pod includes two parts, a sidecar proxy and a user container. And the user container is the one that really executes the application functions. The sidecar proxy provides a bunch of important functions like queuing, metrics collection, doing health checks, all of those that are used to support the control plane. And there's a message broker or a front-end proxy, which provides routing and load balancing functions. And it also provides function chaining support, as we will see. And with function chain support, users can call a group of functions based on a certain sequence. And the ingress gateway here works as the entry point for the entire serverless cloud. And in this control plane, what you see is a placement engine that is used to find a node for a function and place it. Oftentimes people call it scheduling. There's an autoscaler that is used to scale functions based on possibly the current traffic load, and a metric server that provides metrics for control plane activities such as placement and autoscaling. So if you look at a serverless edge, and the reason that we want to look at this with a fresh eye is because we want to look at whether all of the design of serverless computing is equally applicable in a resource-constrained environment like in an edge cloud. Resource-constrained in the sense of you have potentially, you want to maximize the demand that you can support given a limited supply of computing capabilities. So serverless does offer a number of advantages over traditional server-based approach, seamless scaling, quick provisioning, and so on. And running serverless at an edge cloud can deliver the serverless functions geographically closer to the end user and benefit edge applications. And we'll talk a little bit about IoT in this context. But if you look at existing serverless platforms, they don't really look at how resources are utilized. They're much more focused on providing capabilities, and a lot of those capabilities are brought together by pulling together existing components. And as a consequence, we see that there is challenges in a resource-constrained environment like an edge cloud. And that limits sort of the benefit that you get out of serverless computing. And we've looked at a number of these open source serverless environments. And in our work, what we've been looking at is Knative. And the reason for that is it's being actively developed by the community. And we look at challenges there. And I believe that a lot of that is still applicable in a number of these proprietary environments as well, which I don't want to admit that I know a lot about their internals. So the first piece of work I want to go over is work that we call MU, which is stands for an efficient, fair, responsive framework to be used in an edge cloud. And it was a paper that we published in SOCC last year. And if I look at some of the challenges that we see with these existing serverless platforms, and we've studied a bunch of open source ones, and many of these are challenges across all of these, at least open source serverless platforms. And the first challenge is sort of an approximate resource provisioning that happens because of existing autoscalers. The reason I'm looking at these specific challenges is because those are the ones we've solved. Certainly there's, the issue of how to manage a number of other aspects as well, but let me focus on the ones that we've worked on. So when I look at autoscalers and how they manage resources and provisioning, the first thing that these existing autoscalers depend on is user input. Users don't have a lot of knowledge of the runtime features of functions, and so they can easily set up inappropriate parameter values. The second is that these designs use a single metric to guide scaling, which really doesn't effectively handle all workloads. And when you look at traffic bursts, they end up being a challenge for these current designs because they're mostly reactive in their provisioning of functions, and that ends up being slow and results in excessive delays for requests and SLO violations. So that's one thing that we've been looking at how to overcome. The second is, if you look at placement or scheduling, as they call it, I prefer to call it function placement. You don't necessarily have fairness as a consideration, and maybe rightfully so in a very resource-rich environment, because you don't have to deal with fairness until you have an issue of resources being inadequate. But when we start looking at a somewhat more resource-constrained environment like an edge cloud, then existing designs focus on ensuring the use of resources from a throughput perspective without really having a consideration of fairness across functions. And this leads to unfair resource provisioning between functions. If you have two functions that have the same SLO and they're going to be placed, the existing approaches may treat one of them unfairly and allocate resources to the first one and leave a subsequent request starved of needed resources. And it impacts it with a lot of SLO violations. A third thing that we've been looking at is how to deal with heterogeneity and dynamics. And especially when I look at an edge cloud that might be put together over time, then dealing with heterogeneity is indeed a concern. It's probably just as much of a concern in a large data center as well. And being unaware of that resource heterogeneity and system dynamics can end up resulting in poor load balancing. If you look at the standard Knative, and this is not unlike what we see in the Kubernetes environment as well, is that you see them using a least connection load balancer, which tracks the queue length at a backend pod and distributes the request to the pod with the minimum queue length. So let's say that there are the pods on node 2 are faster than the pods on node 1 because node 2, say, has better hardware. Before distributing the request, the load balancer collects the queue length in the pods, and using this least connection policy, the load balancer then selects the pod with the minimum queue length, right? And if pod C is faster than pod A, this can end up being a poor decision. And so we don't really have a good way of handling resource heterogeneity. Another issue is dealing with dynamics. If you assume a homogeneous environment, there is a very popular approach for handling scale, which has to do with this power of 2 random choices. And all the pods here, even if they have the same execution time, because of this random selection of 2 pods and collecting the metrics, pod A would end up being chosen, which fails to sort of recognize that, hey, pod D would have been a better choice. And so it's a good idea to track system dynamics across all the nodes to minimize response time. Obviously, the question that people ask is, well, that is a challenge. The whole idea of doing sampling is to deal with scale. And we've tried to overcome that, as you'll see in a moment. So the last challenge that we've looked to overcome is the idea of approximate metrics collection in a standard serverless environment like Knative. Knative relies on pod metrics to guide its resource management. But existing designs, what they do is they use a random sampling approach to address the scaling problem, which leads to an inaccurate view of the system status and potentially negative impact on resource management. And that's why we have been looking to see how we can get a precise, lightweight, but scalable metrics collection mechanism for serverless platforms. So I want to give you sort of an overview of how we've designed Mu. And we've designed and implemented a number of these different building blocks in Mu to deal with the challenges that I went over. To deal with this imprecise resource provisioning, we developed a SLO-aware autoscaler, and as an integral part of that, have an incoming rate predictor to accurately and proactively allocate functions. The second thing for placement, we used this notion of dominant resource fairness and use that to determine how to do placement and improve fairness at this somewhat resource constrained environment. And then the third is that we designed a smarter load balancer to handle resource heterogeneity and system dynamics. Finally, for metrics collection, we redesigned the Knative metrics collection mechanism to achieve accurate metrics collection by piggybacking them with responses to minimize overheads. So in that sense, this sort of reflects the way ECN works, in that we collect, along with the responses, all of the metrics that we can get from the function pods. So I'll go through each one of these a little bit. First is this SLO-aware autoscaler. The primary idea of our design is to let users provide a latency SLO, which is much more meaningful compared to providing internal configurations such as a maximum concurrency level or a maximum request rate that users are currently required to provide. To achieve more precise resource provisioning, our autoscaler functions, factors in both incoming rate and the queue length. And that ends up giving us a much more informed measure than the inaccurate single metric that they typically use in Knative. And our autoscaler also utilizes the average execution time that is estimated by the function pod to ensure that we meet the SLO without over allocation of resources. To try and avoid the penalty for when you have a long period that it takes for you to provision pods, what we did was to have an incoming rate predictor, and that helps us to provision adequate resources in case of traffic bursts. It's not perfect, but what you'll see is that we are able to mitigate the provisioning time because our predictor is able to use a simple online linear regression model to predict the incoming rate based on previous observations. And this makes our predictor reasonably lightweight and most importantly, fast enough to be able to give us a reasonable predictor for provisioning. And to improve this prediction accuracy, our predictor uses a multi-arm bandit approach by simultaneously running multiple model instances with different hyperparameters. And we dynamically select the model with the minimum running error. The next thing that we did was a placement engine. And to achieve a fair resource allocation, our placement engine uses a two-stage heuristic algorithm to place these function pods. The first stage of the algorithm deals with resource fairness between serverless functions. And we use this notion of dominant resource fairness to select the function that's built around this notion of max-min fairness. And in the second stage, we deal with resource efficiency between nodes. So this combination is very much like what we do in congestion control. And here we consider different scoring algorithms in our work, like alignment, worst fit, best fit, and so on. They're all pretty close. We use one of them, alignment, to reduce resource fragmentation and minimize unfairness. So our placement engine calls these two stages iteratively until there are no resources left or all functions are placed. For our load balancer, we want to be aware of resource heterogeneity and dynamics. So it uses extra metrics to estimate the response time for each pod. And this helps us better differentiate fast and slow pods in the system. In addition, our design uses piggyback metrics of each pod instead of randomly sampling the metrics of two pods, which helps us track system dynamics more closely. And the main thing that you'll see is our metrics collection, where we seek to provide more precise metrics collection to reflect the latest system state and achieve good scalability. And our first customization in metrics collection is to provide additional metrics such as the departure rate, a confidence in that estimate, both of which can be used to support better load balancing and auto-scaling decisions. Our second customization is piggybacking the metrics in each response header instead of sampling the metrics and having another thread to consume CPU to go off and collect those metrics from every pod. So the ingress gateway sends a request to a function pod. The function pod processes the request and returns a response. And before the response is returned to the gateway, the queue proxy in the pod updates the metrics and piggybacks the metrics in the response header. And those metrics are extracted by the metric server in the ingress gateway and forwarded to the autoscaler for scaling decisions. So our piggybacking approach has a number of advantages. First, it gets precise per pod metrics compared to the sampling approach. It can accommodate heterogeneity and system dynamics, and it eliminates the need for explicit metrics collection tasks, which makes it scale to a larger system. There's a bunch more details on these, but I think you can look it up in the paper. But what I want to do is give you a sense of how well our approach works relative to this default Knative approach. So let's look at a system level evaluation of mu. We focus on the comparison with default Knative. And to understand the behavior of different K-native autoscalers, we consider both this RPS based measure that they use, as well as the concurrency based autoscaler that they also use. So CC is the short form that we use for concurrency as we go further when we look at some graphs. The scaling targets for RPS and concurrency, we carefully configured them to make sure that the comparison is fair, and the system is configured to be slightly overloaded to mimic a resource-constrained edge environment. And we used a couple of functions that people saw in the Microsoft Azure cloud. It's a workload that they put out in their ATC paper in 2020. And we labeled them as workload 1 and 2. And our discussion of overall system performance focuses on latency, fairness, the efficiency of pod allocation, and SLO performance, as you see. So the first point is looking at latency and fairness. As you can see in the response time CDFs that we have here, mu has pretty good control over the response time. That is the red line in each of these graphs. It keeps the tail latency within the SLO for both the workloads 1 and 2, as you see with the red lines. On the other hand, if you look at K-native approach, it results in much larger response time tail, which isn't very good. But more importantly, what you see is that if you look at fairness, K-native treats both these workloads quite unfairly. On the other hand, with mu, we get much better fairness. If you look at workload 1 and 2 being treated more or less equally. With standard K-native, you really treat workload 2 quite unfairly compared to workload 1. And what you will see as a result is a lot of SLO violations. Let's look at the latency. And to understand that latency, let's look at the time series for the response time. We'll find that with RPS and concurrency, it results in a large number of requests seeing very high delays at the start of the workload, which is not really good. However, if you look at mu, we maintain fairness between the workloads for the entire experiment across both of these workloads. So in terms of latency and fairness, we see mu being much, much better. And we also notice, of course, that there are some error responses that come out of mu. Those are these 503 errors, as they call it, and that occurs in the beginning when there is an occurrence of traffic bursts. So we feel that there's a good justification for it. So to understand what is the reason for that, we look at understanding the correlation between those 503 errors and traffic bursts. So let's look at the pod count time series of mu. Okay, what we focus on is the first 200 seconds. During this period, the predictor really hasn't yet learned the characteristics of the workload. And in addition, the system has to quickly scale up from having a single pod to over 20. And this takes time. And those are the main reasons for these 503 errors. And as we can see, most of those errors happen when the burst arrives in the first 200 seconds, which indicates that correlation. So, and what we see as a result is that it's during that time that we end up seeing these errors occurring. What I show in the table here is that mu achieves much better SLO than this standard K-native approach. The main reason is that mu uses a SLO-aware admission control and returns these 503 errors when there's a traffic burst. And we feel that that's a sensible approach to shed the load judiciously. This avoids the buildup of a large queue with the arrival of the burst, that queue will persist. If we return these errors, the request will be retransmitted anyway, and overall we get much better quality of experience. And we also need to emphasize that those errors result in a limited negative impact and overall gives you much better SLO. And the 503 errors returned by mu really impacts a relatively small number of requests, which are less than about 5%. And when we look at the standard Knative approach, although they do not have any errors, they build up a large queue, resulting in very long latencies, and 25 to 30% of the total requests end up failing to meet the SLO. If you look at pod allocation also, mu uses far less resources than the standard Knative approach. And this is because the goal of mu is to meet SLOs, not necessarily minimize response time. And its predictor helps it judge that workload. In addition, mu fairly decides the requested pod count based on resource availability. If you look at, on the other hand, the requested pod count by the standard Knative approaches, they end up being unattainable and clearly unfair. For example, the max pod capacity in the system was 48, but concurrency-based approach tries to request pods 2 to 3 times more than the actual resources. So overall, we achieve a lot better latency and fairness and less resource consumption and better SLO, which makes it really helpful from the point of view of a resource-constrained edge cloud. So using that as the basis, we started looking at how can we support things like IoT, and I want to talk about a couple of pieces of work that we've done in this space. So let's start by looking at IoT. We all know much of this about creating a smarter environment and so on. And IoT applications still have constraints, like they want low cost and low power consumption and low latency still, requiring backend support. So serverless computing and edge clouds ideally match this IoT application need for some of these desirable features, especially from the point of view of low cost and trying to still meet some low latency requirements. So we want to look at how we can have a serverless edge cloud that meets these IoT application needs better. Let me go on. So the first building block I want to look at when we look to support IoT applications is the sidecar proxy that we learned from doing our work on mu. You want to have that, especially not only for collecting metrics, but also for having a service mesh. In a serverless environment, you can have a large number of serverless functions, and it'll be a challenge to manage this number of functions at the same time. And that's the reason that you end up wanting to have a service mesh. And that service mesh is basically a configurable infrastructure layer that handles interactions between functions in a chain. And it's built usually on top of these sidecar proxies. Where did I? Okay. And that sidecar proxy helps us to have a service mesh that's able to control these functions without coupling them very tightly. And the sidecar proxy provides a lot of important functions, both in the control and data plane for monitoring, routing, and load balancing. So we wanted to look at that in particular. There's a second piece, which is having to deal with adaptation between these protocols that IoT environments use and what we typically have in a serverless cloud. We end up needing to have a protocol adapter, especially what we looked at here was MQTT to HTTP. Most serverless frameworks are HTTP oriented, and the interaction between the serverless functions are performed through a REST API. But IoT devices adopt other protocols like MQTT protocol using and publish subscribe to reduce bandwidth and possibly to save power. So you end up needing an MQTT to HTTP adapter, and you need to do that to handle this protocol compatibility. So if you look at using Knative and say, hey, how can I support all of this? And overall, if you look at using these existing building blocks with Knative, yes, you can provide a serverless environment, but there are a bunch of limitations that we found with that approach. One is that this queue proxy that you see is constantly running, okay? And so these constantly running components in the system end up being heavyweight and introduce quite a lot of CPU overhead. And as we are running these IoT applications in this resource-constrained edge environment, we really need to be aware of resource usage and think about how to save resources as much as we can. So to do this, we use eBPF-based approach. And this eBPF-based approach is very convenient because what we see is that it's really an ideal capability for event-driven execution of code in the kernel, and it can naturally work in the serverless environment. So we developed an event-driven proxy and replaced this heavyweight Q proxy in Knative with a lightweight eProxy as an enhancement. And so what I want to do is give you a little bit of detail about eBPF. This is a user-driven sandboxed bytecode that is executed in the kernel, and it's naturally event-driven. And it only is executed on a new event. There are a number of hook points in the kernel that you can attach eBPF programs, such as system calls, at the socket, in a network device driver, and they can be used to support a bunch of capabilities like packet processing, filtering, traffic monitoring, and so on. And so eBPF is convenient for this event-driven execution. It also provides a user to kernel space interaction mechanism, and that's using this eBPF map. And we can use that to perform metrics collection and configuring routing rules and so on. But eBPF is not universal. It has a number of constraints. Okay, eBPF programs are not allowed to have loops, must run to completion to ensure kernel safety and so on. And limited instructions are allowed in a single eBPF program to guarantee that kernel stability. So the constraints of eBPF requires developers to carefully write their code. So we built this monitoring service using this thing that we call the eProxy. Here's a design of it. The eBPF programs are attached to the virtual Ethernet of the function as an event-driven component. It can record metrics for each of the packets, such as the number of requests per second, execution time, and so on. And then these collected metrics can be stored in these eBPF maps, and a metrics agent can then scrape those metrics stored in the eBPF map and update it to the control plane periodically. So I'll briefly touch on a little evaluation before I get on to some more in-depth work. So we did a small little experiment with a couple of nodes in Cloud Lab. If you look at the CPU overhead breakdown first, the CPU usage of the Q proxy with Knative, what we see is that it's very close to the CPU usage of the function container itself, which is a lot of excess CPU consumption in a resource-constrained environment. When we replace the Q proxy with this E proxy, what we see is that we reduce the CPU usage by about 50%, which clearly shows the lightweight feature of the C proxy. And yes, using this MQTT protocol introduces a small amount of extra overhead compared to HTTP, but by doing that, you introduce protocol compatibility. And this is one also that we think can be handled through this event-driven execution, which is what we then said, let's look at how we can use this event-driven execution to build a overall more capable data plane. And so that's the thing that I'm going to briefly touch on. I know I only have about 10 minutes, so I'll try to go as quickly as possible through that. So one of the things that we wanted to do was to say, let's carefully look at all of the overheads for serverless computing, okay? And we said, let's look at it in the context of Knative first, where we have to support function chains to meet the requirements of these microservices. And so this is a typical serverless function chain setup with a couple of functions. And we ordered the processing overheads involved in the serverless function chain, including number of copies, context switches, interrupts, protocol processing, serialization, and deserialization. So in the first step, an external client sends a request to a function or to this function chain in the serverless cloud. And the request is intercepted by this ingress gateway, which then performs the task like authentication and request routing. And this processing generates a data copy, a context switch, 3 interrupts, and has to do protocol processing and 1 serialization task. And then the second step, the request is routed to and then queued in this message broker front-end proxy, and it's registered as an event. This processing generates a couple of additional copies, a couple of context switches, lots of interrupts, protocol processing, and so on. And then depending on the routing configuration of the function chain, the message is sent to an active pod of the head function in the chain. And in the fourth step, the function pod is invoked to process the incoming request. And when the request message is processed by the first function, a response is returned and queued in the message broker front-end proxy. So that can be registered now as a new event for the next function in the chain. And the last step, the message broker front-end proxy sends this new event to an active pod in the next function chain. So processing in step 3, 4, 5 generate the same amount of overhead, including a number of copies and context switches and so on. So this current design of serverless function chaining relies on the composition of these existing networking components, such as to support asynchronous reliable message exchange between functions. And traffic within the chain has to go through this message broker front-end proxy every time, and involves crossing user kernel boundary a number of times. So this inevitably introduces a lot of additional overhead. And in addition, as the chain becomes more and more complex, the overhead increases, resulting in very poor scaling. So if you look at overall, the takeaways that we have from the point of view of this overheads is that there are, first is there's lots of extra data copy. And just like we did in our OpenNetVM NFV platform, that's one focus that we had. And the second is context switches And the third is interrupts, which we've been trying to avoid for ages now, that are generated within, and I'm going to focus a lot on being inside the serverless function chain. So as you see, about 80% of data copies, context switches, and interrupt overhead come from networking within the function chain, not going in and out of the serverless platform. And then the second thing is a lot of excessive duplicate protocol processing. Networking within the function chain, again, accounts for about 75% of the total protocol processing overhead. And the third is unnecessary serialization and deserialization. Since serverless functions mainly work with HTTP REST API, right? There is a need for additional serialization and deserialization operations to convert this application data to or from network byte streams. And as you can see, each step within the function chain introduces a couple of these serialization and deserialization operations. And the last one is this individual constantly running heavyweight component. And the typical example, as we saw before, was the sidecar proxy. And the presence of the sidecar proxy introduces a lot of overhead. Just looking at one step, that step 4 that introduces a couple of data copies, 2 context switches, and 2 interrupts. So we said, hey, is this only unique to Knative's Q-proxy? So to understand that impact on the data plane performance, we said, let's look at a bunch of different sidecar proxies, including the Envoy sidecar from Istio, the Q-proxy from Knative, and there is another one called the OF Watchdog from OpenFaaS. And as we saw, having a sidecar proxy results in anywhere between 3 to 7 times reduction in throughput and 3 to 7 times higher latency and a huge increase in CPU cycles per request. And when we look at the CPU overhead breakdown, what we see is about 50% of the cycles are consumed by the kernel stack for the sidecar proxy. And we really want to try to avoid that. So through our auditing, we find that this loosely coupled construction of existing serverless components results in a lot of unnecessary processing overhead. And that makes this serverless computing very inefficient and resource hungry. And so this poor data plane design and having these individual constantly running components in the function chain, it requires us to look at how can we build a more streamlined responsive serverless framework, in addition to all the control plane components that I talked about in the previous part of my talk. So what we said was, let's see how we can reduce the consumption of the server in serverless computing. And for this, we have been looking at how to build a somewhat more streamlined framework and to build a higher performance environment. And for this, we took what we had built before with our NFV platform with OpenNetVM, look at how we can have a high performance shared memory processing framework and take advantage of this lightweight event-driven capability that we looked at just a bit before, and look at how these two innovations can be brought together. And on top of that, there's a number of other optimizations we thought about. One, to reduce the excessive overhead with these current serverless function chain. These two core innovations improve the data plane performance so that resource consumption becomes really strictly load proportional. Okay, and in addition, we introduce a gateway component to provide consolidated protocol processing. And we still do take advantage of the kernel protocol stack, but look at judiciously executing that only when necessary. And importantly, we avoid duplicate protocol processing within the function chain. And to improve scalability of the function chain, we have this notion of direct function routing. It's not anything new. Others have used it before, and especially in a NFV type context, we use that extensively. We want to do the same here and bypass the intermediate networking component. So in this case, we bypass even our gateway that we've built when the request is transmitted within the function chain. And to remove this individual constantly running sidecar proxy, we use this eBPF-based event-driven proxy, but there are two different purposes that we have, one for metrics collection and another one for packet descriptor delivery, and we call this an E proxy and an S proxy. We apply the eBPF-based data plane acceleration for external communication outside the function chain as well, between our gateway and the ingress gateway port. And also what we did was for the specialized use case like IoT, where you need this additional protocol adaptation, say for MQTT to HTTP protocol adaptation, we optimize that protocol adapter again by running it as an event-driven component that is attached to our gateway and avoid the unnecessary network communication between components. I would be tempted to walk through each one of these, but given only 2-3 minutes, I want to skip through these. At some point, you can look at these in detail in the future. What I want to do is say, let's look at what's the benefit that comes out of all of this. So if you look at the overhead auditing with our design, we compared the same function chain setup as we saw with Knative. And what we see is 0 data copies, 0 additional protocol processing, and no serialization, deserialization overhead, of course, within the function chain. And we called it SK message for socket messages to generate context switches. We do have context switches and interrupts, which adds latency for processing. And the total number of, but the total number of context switches and interrupts for our design is still much less than that of the base Knative design. And that way, this event-based shared memory processing brings a substantial reduction of overhead for communication within the serverless function chain. There's a bunch of evaluation that we did. One was using somewhat a complex function chain. A lot of people have been using this, called this online boutique from Google. And it has 10 different functions with different CPU service times and 6 different sequences of function chains provided by the online boutique workload. There's a couple of other workloads as well that we looked at, but let me just go through this one slide on looking at how the online boutique workload behaves with our approach compared to using Knative. And actually, we looked at 2 different alternatives. One was using this event-driven proxy design and using this SK message design that I talked about. But we also wanted to say, well, what if we did use DPDK instead to have shared memory? And we compared all 3 of these. And we set the concurrency level for Knative at about 4K, because that's about the limit that it can handle. Even that, we see that there is a little bit of variability. So we pushed it as far as we could. For our 2 designs, for DPDK-based design with polling, as well as our event-driven shared memory processing, which we called it SK message because of the socket interface that we use to send messages for the shared memory design. We set the concurrency level at about 12K to generate much more intensive traffic. And if you look at the throughput and latency comparison in this figure, Knative's RPS varies over time, and that's because it's somewhat overloaded. If you look at this time period between 50 and 72 seconds, the response time of Knative increases quite significantly, and that contributes to the large queuing at that Knative's gateway and has a large tail latency as a result. On the other hand, if you look at DPDK and SK message, it maintains a stable RPS about 3 times as much as Knative on the same platform. And that's because the shared memory processing overhead is a lot less and communication within the function chain is so much more efficient, so that you can get much better throughput in terms of RPS and latency compared to Knative, even with a much higher traffic load. There's a bunch of more results. I want to skip through. I can keep going on and on and on. But I'll share the slides and you can look at it later on. So overall, resource management in these open source serverless frameworks, and I believe that that's representative of what we typically see in other proprietary platforms as well. They need improvement if you want to operate in a somewhat more resource-constrained environment like an edge cloud. And our new design is one example, where using an SLO-aware autoscaler and an incoming rate predictor achieves more precise resource provisioning. And this DRF-based placement engine does achieve much better resource fairness. And we can factor in resource heterogeneity and system dynamics in load balancing. And the key for scalability in this kind of environment was we piggybacked the metrics to get much more precise and scalable metrics collection. So that was the control plane design with Mu. And then we said, let's look at how we can get higher data plane performance while reducing the inefficiencies that we see in these current open source serverless environments, and using the shared memory processing to optimize the data pipeline within a serverless function chain is tremendously helpful. And this event-driven processing using eBPF to improve resource efficiency is also very helpful for us in taking away many of the heavyweight components in serverless platforms. I'm sorry I went over. I planned for an hour. I probably should have stopped a little bit earlier. Thank you very much for listening. I'm happy to take any questions you folks might have.
Thanks, KK. That was very interesting. I think we are -4 minutes, but it's Friday evening, so if people need to leave, then they need to leave. But there are several with questions. Abhishek, you're first in line.
Hi, Professor. Abhishek from University of Oulu, Finland. It was a really great talk. I learned quite a bit on heterogeneity, how to manage that, and auto scaling. So I have 2 questions. So when I look at the current implementation, by AWS Lambda function, Google Cloud function, and Azure, the developers have to use the flow of the function using their library. So I'm kind of worried that there's no cloud agnostic. I mean, the developers, it's very specific to one service provider.
Yeah, Abhishek. Yeah, Abhishek. I teach this in my class also. You know that what we want is to say, hey, you build a function. The whole idea of the serverless is that you just have to focus on building your code for your function, and then you should be able to run it, right? The difficulty is that the tooling that you have to utilize, that's all very cloud provider specific. And you end up being sort of more and more tied to a particular cloud service provider. And that's something that we should look to get out of. But I've noted that is indeed a issue that we see. So we are in the somewhat early stages of this, Abhishek. And I think, there will end up being standards that will be created for APIs so that you can have the flow that is much more generic, that you can then be able to move from one cloud provider to another.
Right.
I assume that's what you were asking, right?
Yes, exactly. That's the okay. And I have one more quick question. So when I look at the serverless, the implementation goes by nowadays like function as a service, and these functions, they could be triggered by many external or internal event sources, which have multiple formats in coding. So to me, it sounds like it creates the multiple entry points for adversaries to gain the control of the system. So the serverless, I mean, I understand the merit. It promotes resource efficiency, but from security point of view, it seems a bit. What are your thoughts on this one?
So, as some of the people who might be on in the meeting know, I do not have any claims to make regarding security because I've deferred to other people, but certainly that is indeed a concern. And ever since I started working in this whole cloud environment, this has been a concern that's gradually been mitigated by having capabilities that the cloud service providers provide. And when you have a function as a service, then you increasingly end up depending on the cloud service provider to provide all of those security protection, because as a function developer, you're only focused on having your function created, and you really are ending up depending on the cloud service provider, very much like we depend on our network service providers to provide us some of the barriers for attacks like DDoS and so on. It's the same thing. But I don't have any more of an intelligent answer than you might have, Abhishek, on that. But it is certainly something that cloud service providers focus a lot on.
Right. Thank you. Thank you very much. That was my questions.
So KK, if I can ask you one very quick question. So you had in your first one in the Mu, you were focused both on SLO as well as fairness. And I wonder whether fairness even matters at all for the end users who are basically the people who are creating these functions, and whether if it's just the SLO that if SLO is being honored, then do they care?
And this is usually the question, right, Nishant? Do I care about fairness? If I get what I want?
Yeah.
And sure, if you get what you want, you don't care about fairness, right? And this has been true of humanity all along, right? If you have a full stomach, what do you care about whether somebody else eats more or less, right? It's only when you do not have a resource-rich environment that you start caring about it, when you can't get everything that you want, right?
Sure.
And so there's a balance here, and this is a balance that we've been trying to strike forever and ever about, meeting throughput goals, meeting latency goals, and what happens when you can't meet those because your resources are over subscribed. And it's only then that you care about fairness, right? The thing, even in our design, right, if you have plenty of resources, we take very little time to place the requests. It's only when we end up seeing that we don't have sufficient resources, that's when we have to spend the time to look at how do we do our fairness allocation, which dimension do we apply, how do we balance across multiple dimensions. None of this matters if you're resource rich.
Yeah, makes sense. And the next, I think Mace has a question.
Thank you very much. The discussion is quite interesting, and this is Mace from University of Essex. And I'm wondering about the trade-off of fairness versus greedy. So in the results that you've shown earlier, are you suggesting that then the K-native current approaches are on the other spectrum of greediness? Or is there inefficiency due to other suboptimalities in the algorithms?
So the algorithms that they use assume that there's plenty of resources, number one. And I don't want to call them greedy as much as trying to meet the sort of, let me try and find the resources that best match the requirements now for this function that I'm placing, so that I can look to optimize how the resources are available in the future in a judicious manner. I don't want to say that their designs are poor, but they are wasteful.
That's the,
and the main concern here is that the whole placement strategy doesn't focus on what would happen if I were to run out of resources, and how do I fairly allocate. And this is the same question that Nishant asked, right? Why do I care about fairness, right? If I didn't care about fairness, a lot of this doesn't matter.
Well, I completely agree, because I mean, one thing when you're talking about why do I care about fairness is because you get consistent performance with fairness, and I'm not suggesting by any means that there is potentially something wrong with the greediness. It's quite interesting to know that fairness is not an objective for Knative, and I'm wondering what would the comparison look with a greedy approach? Because one thing, for example, we discovered when looking at other fields, with, for example, blockchain, is that honesty. I mean, the end of the spectrum on the honesty side of things is not necessarily favorable, equivalently to the other end of dishonesty. And I'm wondering if there is a trade-off comparison with the greedy approach, and there is a point in the middle where you see an optimum position in terms of fairness versus greediness.
See, I think that's what we try to do with a number of these. I don't know if one would say, I don't know how to reason between greediness and fairness and trying to balance the two. I mean, they both tend to be pulling in opposite directions, right?
That's correct, yeah.
And the concern for me is not only about fairness. You know, a lot of the fairness metrics even that we think about, even in congestion control, is long-term fairness, which to me is inadequate as a measure. We really need to look at it on a, you know, over time, because if I starve for a day and then I get a lot of food the next day, that doesn't help, right? I want it to be, as my requests come in, each request I want to make sure that it gets served reasonably. If you look at what is happening with these approaches like Knative's approach, whether it is RPS or CC, either of them, look at the kind of dynamics that you see. right? In terms of response time, it's huge for some period of time. All these requests are going to be totally unhappy, right? If they're sitting around waiting for essentially, 50 seconds.
Yeah, I absolutely see your point in there.
But I don't know how to reason about striking a balance between greed and fairness, because they are, truly, in my mind, contradictory. And greed is perfectly fine when you have a resource-rich environment where you don't worry about, running out of resources. And greed is absolutely the wrong thing when you have resources that are constrained and oversubscribed.
Yeah, that sounds like a good point on which to maybe end this. Very philosophical, fundamental thing which you can't square a circle kind of thing.
Well, look at what is happening in the world right now, right?
Oh,
Anyway,
yeah. So thanks so much, KK, for this talk. And I guess we'll wait until you say yes before we upload this onto YouTube.
Thank you very much, Nishant. I really appreciate that understanding.
Yeah. Have a great weekend. Bye for now.
Thank you very much, folks. Thanks. Bye.
Thank you very much. Bye-bye.
Bye-bye.